This class discusses binomial distribution. Some discrete random variables are very important and have broad applications in practice. We will give them a name. Binomial random variable and binomial distribution are typical examples. Let's first check what Bernoulli trails are. Bernoulli trails are repeated trails of experiments satisfying the following three conditions. First, each trail has two possible outcomes. For example, tossing a coin has only two possible outcomes, head or tail. The gender of a baby has only two possible outcomes, male or female. Guessing the answer of a multiple choice question has only two possible outcomes, correct or wrong. Usually, one of the outcomes is referred to as success and the other one is referred to as failure. Second, trails are independent of each other. It means that the outcome of one trail will not affect the outcome of the other trail. When tossing a coin, the result of one toss is independent of another toss. Third, the probability of a success remains the same from trail to trail. This probability is called the success probability and denoted by P. When tossing a coin, the success probability is 0.5. For genders of a newborn baby, the success probability is also 0.5. For guessing the answer of a multiple choice question, assume that each question has four possible answers. The success probability is 0.25. Let's look at another example. A person of age 20 years has about a 80% chance of being alive at age 65 years. Suppose three people of age 20 years are selected at random. It is a sequence of three Bernoulli trails. We need to check the three conditions for Bernoulli trails. Each trail has two possible outcomes. Here we have only two possible outcomes, alive at age 65 or dead before age 65. Second, trails are independent of each other. Here we have three different persons. It is reasonable to assume that whether they are alive or dead at age 65 is independent. Third, the success probability remains equal. Here, success means alive at 65. According to the information, the success probability is 0.8, which is the same for these three persons. Therefore, it is a sequence of three Bernoulli trails. For this sequence of three Bernoulli trails, there are 8 possible outcomes. Use S to denote alive and F for dead. The 8 possible outcomes are listed in the following. We can calculate the probability of each outcome. For example, what is the probability of SFS? Because the three trails are independent, by the special multiplication rule, probability of SFS is the product of each probability, or probability of S, probability of F, probability of S. According to the information, probability of S equals 0.8. Probability of F is 1 minus 0.8 equals 0.2. We know that probability of SFS equals 0.8 times 0.2 times 0.8 equals 0.128. Similarly, we can calculate the probability for each possible outcome. This tree diagram organized all the calculations. It follows the same reasoning as what we did in the previous slide. Because the three trails are independent, we simply calculate the probability of each trail and then multiply them together. Let X denote the number of people of the three who are alive at age 65. X has 4 possible values, 0, 1, 2, 3. To get the probability of X, we just need to figure out which outcomes it contains. For example, X equals 0 means all dead. It corresponds to only one outcome, FFF. Hence, the probability of X equals 0 is the probability of FFF, or 0.008. X equals 1 means 1 alive and 2 dead. It corresponds to SFF, FSF, FFS. We need to add the corresponding probability together. So, probability of X equals 1 equals 0.032 plus 0.032 plus 0.032, which is 0.096. Similarly, we can get the probability of X equals 2 and the probability of X equals 3. The probability histogram is also displayed in the slide. And the random variable X is essentially a binomial random variable, and its distribution is called binomial distribution. First, we need to introduce some notations. The product of the first k positive integers is called k factorial. It is denoted by k followed by an exclamation mark. In terms of symbols, k factorial equals 1 times 2 times 3 up to k. For example, 5 factorial equals 1 times 2 times 3 times 4 times 5, which is 120. We also define 0 factorial is 1. For a positive integer n and a non-negative integer x, the binomial coefficient is denoted by n on top of x in the parentheses. It reads as n choose x. It equals n factorial divided by x factorial and n minus x factorial. Or it is the ratio of two products. The numerator is the product of x integers, counting down from x. The denominator is the product of x integers, counting up from 1. For example, 5 choose 3 is the ratio of two products. The numerator is the product of three numbers, counting down from 5, so they are 5, 4, 3. The denominator is the product of three integers, counting up from 1. So they are 1, 2, 3. Do the math. The value is 10. Let X denote the total number of successes in n Bernoulli trials with success probability P. Then the probability distribution of X is given by this formula. It states the probability of X equals X. Notice that the possible value of X is 0, 1, 2, and up to n. The first item in the formula is the binomial coefficient we just introduced. The random variable X is called a binomial random variable. The distribution is said to have the binomial distribution with parameter n and p. We can use this formula to check the number of people of the three who are alive at age 65. It is a binomial random variable with parameter n equals 3 and p equals 0.8. Apply the formula to get the probability of x equals 1. The binomial coefficient is 3 choose 1 and its value is 3. Do the math, we get 0.096, which is the same number as we got before. This slide lists all the key steps to calculate a probability involving binomial random variables. Firstly, we need to make sure that it is indeed a binomial random variable. Recall that a binomial random variable is the number of successes out of n trials. Make sure to check the three assumptions of Bernoulli trial, namely two possible outcomes, independent trials, and constant success probability. After that, choose one possible outcome as success. Identify the parameters n and p. Notice that n is the total number of trials and p is the probability of success. Then we are ready to apply the formula to calculate probabilities. We have discussed this example before. There is roughly a 80% chance that a person of age 20 years will be alive at age 65 years. Suppose that 3 people of age 20 years are selected at random. Let X denote the number alive at age 65. We claim that X is a binomial random variable with n equals 3 and p equals 0.8. Let us calculate the probability that the number is exactly 2. Replace x by 2 in the formula of probability for binomial random variables. The binomial coefficient is 3 choose 2 and its value is 3. If you are not sure, I also include the details in the slide. The binomial coefficient is the ratio of two products. In the numerator, we count down from 3 for two integers. In the denominator, we count up from 1 for two integers. Therefore, the result is 3. Do the math, we get 0.384. The probability that the number of exactly 2 is 0.384. Find the probability that the number is at most 1. Here, we want to find the probability of x less than or equal to 1. Notice that the possible value of x is 0, 1, 2, 3. So, x less than or equal to 1 means x equals 0 or x equals 1. We can find the probability of x equals 0 and x equals 1 separately and add them together. The first binomial coefficient is 3 choose 0, which is 1. In the bottom, I list some tricks of binomial coefficient. N choose 0 is always 1. N choose 1 is always n. And n choose n is always 1. Therefore, these formulas can be easily obtained by the definition of binomial coefficients. You can verify them by yourself. In general, the probability of less than or equal to a number is called a cumulative probability. In this example, we just calculated the cumulative probability of x less than or equal to 1. Find the probability that the number is at least 1. This is a typical case that applying the complementation rule can make the calculation easier. Of course, we can use the same strategy as before. Notice that x greater than or equal to 1 means that x equals 1 or x equals 2 or x equals 3. We can calculate the probability of each of them and then add them together to get 0.992. However, the possible value of x include 0, 1, 2, 3. Hence, x greater than or equal to 1 means that x is not 0. If you apply the complementation rule, the probability of x greater than or equal to 1 equals 1 minus probability of x equals 0. We only need to apply the formula once. The calculation is much easier and the answer is the same. In practice, we need to be flexible about which approach to use. Try to find the easiest approach to solve a problem. In this slide, we show some histograms for binomial distributions. The first parameter n is always 6. However, the success probability p is different in these three histograms. It is 0.25 in the first diagram, 0.5 in the second diagram, and 0.75 in the third diagram. We see that when p equals 0.5, the shape of the distribution is symmetric. When p is less than 0.5, the shape is right skewed. When p is larger than 0.5, the shape is left skewed. No matter what value p is, the distribution is always unimodal, or it has only one peak. We can calculate the mean and standard deviation of a binomial random variable. Here, I simply state the results as formulas. You can try to verify them following the definition of mean and standard deviation. The mean of a binomial random variable is n times p. It makes sense. We have n trials, and each succeed with probability p. Therefore, we expect to have n times p successes. The standard deviation is the square root of n times p times 1 minus p. We can see that when p equals 0.5, the standard deviation is maximized. When p moves away from 0.5, the standard deviation will become smaller. We may apply these formulas to calculate the mean and the standard deviation of x in the example we discussed before. Recall that x is a binomial random variable with parameters n equals 3 and p equals 0.8. Therefore, the mean of x is 3 times 0.8 equals 2.4. Its standard deviation is square root of 3 times 0.8 times 0.2, or 0.7. In practice, as long as we can identify that a random variable is binomial, we can always apply these formulas to calculate the mean and the standard deviation. We can calculate the probability using Excel. The name of the function is binom.disk. It has 4 arguments. The meaning of the first 3 arguments is clear. The last argument has only 2 possible values, true or false. It tells Excel whether you want probability or cumulative probability. True corresponds to cumulative probability and false corresponds to probability. Let's look at another example. Roll a die 10 times. Find the probability of the following events. Those events are about the number of 6. We may let x be the number of times we roll a 6 in 10 rolls of a die. First, we need to check whether x follows a binomial distribution. Each roll has 6 possible outcomes. However, because we only care about the number of 6 in this problem, we may treat 6 as success and other values as failure. By this way, we reduce the 6 possible outcomes to 2. Each row is independent of each other. The probability of 6 of each row is 1 over 6 and remains constant. Therefore, they are Bernoulli trails, and x is a binomial random variable. The parameters are n equals 10 and p equals 1 over 6. For each question, I include the detailed calculation and also Excel function. For the first question, we want to calculate the probability of exactly 1/6. It means the probability of x equals 1. We can directly apply the formula for binomial distribution. If you use Excel, the last argument of the function is false because we want the probability, not cumulative probability. For the second question, we want to calculate the probability of at most 2 6s. This is the probability of x less than or equal to 2. It is a cumulative probability. When using Excel, the last argument is true. If we do the calculation by hand, x less than or equal to 2 means x equals 0, x equals 1, and x equals 2. We simply apply the formula for binomial distribution 3 times to get the probability of x equals 1, x equals 0, and x equals 2. The final answer is 0.7752. This question asks the probability of less than 2/6. Notice that x less than 2 is equivalent to x less than or equal to 1. Therefore, the first argument in the Excel function is 1, not 2, because when calculating a cumulative probability, it is the probability of x less than or equal to a number. So, you need to pay attention to the difference between less than and less than or equal to. The next question is the probability of at least 2 6. At least 2 6 means x greater than or equal to 2. For problems involving larger than, it is usually easier to apply the complementation rule. Here, the probability of x than or equal to 1 equals 1 minus probability of x less than 2. Or equivalently, 1 minus probability of x less than or equal to 1. It is exactly the complement of the probability of less than 2 6. In this question, we need to find the probability of at least 2 and at most 4 6, or the probability of x greater than 2 and x less than or equal to 4. The corresponding value of x include 2, 3, 4. So we just add the probability of x equals 2, x equals 3, and x equals 4. Be careful when using Excel. The first argument of the first function is 1. Because when evaluating this probability, we need to represent it as the difference of two cumulative probabilities. Let's check an application of binomial distribution in the real world. Not everyone who paid for an airline ticket will actually show up for the flight. The airlines know that and sell more tickets than they have seats on the plane. Overbooking is also a common practice in car rental and hotel reservations. Suppose that 10% of all the people who buy an airplane ticket don't show up for the flight. An airline has a capacity of 150 seats for a certain flight and sells 160 tickets. Find the probability that everyone who shows up for the flight will get a seat. To answer this question, we make the simply assumption that all ticket holders act independently. Then, each ticket holder is a ballooning trail with probability 0.9 for showing up to the flight. Let x be the number of people who do show up when n equals 160 tickets are sold. Then x is a binomial random variable with parameter n equals 160 and p equals 0.9. Everyone who shows up for the flight will get a seat. It means that x is less than or equal to 150. Then the possible value of x include 0, 1, 2, and up to 150. If we do the calculation by hand, we need to calculate the probability of x equals 0, x equals 1, and up to x equals 150. Then add these probabilities together. It is tedious, but it seems no easier way. Of course, we can use Excel. Use the function binom.dist. The first argument is 150 because we want to know the probability less than or equal to 150. The second argument is 160 because the parameter n equals 160. The third argument is the success probability p. The last argument is true, which indicates that we want cumulative probability. The probability is 0.9641. Therefore, with probability 0.9641, everyone who shows up for the flight will get a seat. Let's consider a different problem. Suppose that another airplane has 250 seats. How many tickets can the airline sell if it is required that with probability of at least 95%, everyone who shows up gets a seat? Similarly, let X be the number of people who do show up when N tickets are sold. Here, X is still a binomial random variable with success probability 0.9. However, the value of N is unknown, which is the number of tickets sold. Now, we need to find the largest number N such that the probability of X less than or equal to 250 is larger than 0.95. One way to find N is to evaluate the probability of X less than or equal to 250 for different values of N. We may start from N equals 250, gradually increase N until the probability is less than 0.95. If you try different value of N, you will find that when N equals 269, the probability of X less than or equal to 250 is 0.962. When N equals 270, the probability of X less than or equal to 250 is 0.94, which is smaller than 0.95. Therefore, the airline can sell up to 269 tickets to guarantee that with probability of at least 95%, everyone who shows up will get a seat. In the last, I want to show you some examples of typical non-binomial random variables. For example, the number of phone calls in one day and the number of car accidents in Highway I-85 in 1 year. To be a binomial random variable, we need to be able to identify ballooning trails. We also need to identify the parameters n and p. However, we cannot identify n in the above problems. The number of phone calls can be 0, can be 1, and can be a very large number. However, there is no upper limit. The same for the number of car accidents. Therefore, they are not binomial random variables.